Hello, everyone. Welcome to the April 23rd edition of Math Stats. Reminder that your homework is due on Monday. So today, we're going to learn about a very similar test called the chi-square test for independence. Now, this is done in a very similar manner to the chi-square test for homogeneity, but we're trying to show something a little bit different. Something that you're going to want to know in a lot of your tests are, I have two variables, maybe it's gender and income, and you want to know, are they independent or is there some covariance? So, or is there some correlation? That is something that's a very important question to ask because independence is what we really want to know is true. So let's get to work. So let's suppose that we have a random experiment that has outcomes that can be classified by two attributes. So we have a random experiment. And it results in outcomes with two different attributes. Maybe it's height and weight. Anyway, the first attribute is assigned to one of k events. And attribute 2 can be attributed to h events. All right, so we're going to let AI intersect BJ be, the outcomes where they fall into category AI and category BJ. And we say the probability of this we're going to call Pij. So we do the random experiment n times. And Yij is going to be the number, it's the frequency, the observed frequency of AI intersect Bj. Okay, so there are kh possible events because you could fall into one of the k categories A1 through AK and the h categories B1 through BH. So what this tells us is that my statistic is a chi-square random variable with kh minus 1 degrees of freedom. And so the null hypothesis is that the probability of these events AI intersect Bj is the probability of AI times the probability of Bj for all possible i's and all possible j's, because that's the definition of independence. So we're going to rephrase this as H0 is our null hypothesis that Pij is Pi dot times P dot j, where Pi dot is the probability of AI, and P dot j is the probability of Bj. So unfortunately, we don't know what the Pi dots are and nor the P dot i's. So we need to estimate them. So we estimate the Pi dots by Pi dot hat with Yi over n, where Yi is the sum of basically all of the outcomes in AI. So this is the relative frequency of AI. Or the observed frequency, we should say. And P dot j hat, we're going to, there's a dot right there, dot right there, is this. And this is the observed frequency of J. So in doing this, we have estimated k minus 1 plus h minus 1, which is k plus h minus 2 parameters. Because when you're estimating the probability of AI, you only need to do this from AI1 through AK minus 1. And when you're estimating the PIJs, you only need to estimate the probability of B1 through BH minus 1. So remember that when we do our chi-square random variable, we'll need to subtract off from the degrees of freedom the number of parameters we estimated. So we get this very lovely expression. And this is a chi-square random variable with kh minus 1 minus k plus h minus 2, which if we do the algebra is k minus 1 times h minus 1 degrees of freedom. All right, so let's put this all to the test. So we're going to do an example. And the following table shows Myers-Briggs personality preferences for a random sample of 406 people in 3 certain professions. Okay, and E is extrovert and I is introvert, in case you don't know. Okay, so let's create this table. We have the clergy, we have MDs, and we have lawyers. We have extroverts and introverts. All right. All right, so I'm going to discuss a little bit about what's happening. Let's say these are the different categories for B. So B1, B2, and B3. And these are the categories A1 and A2. So we can estimate all of these probabilities. So we estimate that the probability of one dot is, well, what's the probability of an extrovert? That's 186 over 406. What's the probability of an introvert? Well, that's 220 over 406. What's the probability of the clergy? Well, that's 107 out of 406. The probability of an MD in our sample, 162 over 406. And last but not least, the probability of a lawyer is 137 over 406. So now we can compute our Q value. So what we need to do for each of these different 6 categories is we need to take the observed minus the expected. So let's talk about the first one, clergy extroverted. So this is 62 minus 406 times the probability of extroverted. Well, the observed probability is 186 over 406 times the probability of clergy, which is 107 over 406 squared over the expected. And we'll do some more of these to see what's going on. Let's look at clergy introverted. That's 45 minus 406 times the probability of clergy, or sorry, of introverted, which is 220 over 406, times the probability of the clergy, which is 107 406 squared over the expected. All right, so let's do some more of these. Let's do MD. So there are 68 MDs who are extroverted. Minus 406 times the probability of extroverted times the probability of an MD. And then let's do MD introverted. So probability of introverted times the probability of an MD, observed anyway. And last but not least, let's do extroverted lawyer. And introverted lawyer. All right, so needless to say, doing this in by hand would be terrible. So what's our null and alternate hypotheses? Well, our null hypothesis is that The occupation and personality preferences are independent. That is, someone's Myers-Briggs extrovert versus introvert is independent of their profession between clergy, MD, and lawyer. So let's take a look at our studio and see if we think there's evidence for that. So let's create our data. Remember, it's done by column. We create a matrix out of it. 3 rows. We see our data here matches that from before, and we do a chi-square test of it. And we get a chi-square value of 8.6492. So we see that our chi-square value is 8.6492. We have 3 minus 1 times 2 minus 1 is 2 degrees of freedom, and it calculated a p-value of 0.01324. So I didn't mention earlier, but alpha was 0.05. So our p-value is less than alpha, and we reject H0 and conclude that personality preference and occupation, at least for these occupations, are not independent. That is, there is some relationship. This test doesn't tell us what that relationship is, but it tells us there is some tendency. They are not independent of each other. We don't know how related they are, but we are confident they are not independent. Of course, anyone who knows things about the clergy and lawyers knows that they're different. There are way more extroverts among the clergy, but how different they are, this test does not conclude. So the data in these tables is stored in what we call a contingency table. The book discusses how to extend this test for independence of 3 or more variables, but we won't cover that today. For now, though, we would like to switch to, well, how do we take this test for independence and discuss how to handle data that is not so easily put into categories? For example, continuous data. And the answer will be the same as before. We just need to create categories. So let's look at an example of some data, which has already been sorted into categories for you. So a sociologist I'm on a roll today. Wants to know if age is independent of movie preference. So they take a sample in young adults, a sample of 93 young adults is taken. And here's the contingency table. So we have drama, science fiction, and comedy. And we took the survey and divided up the ages into these years. and we collected the following data. So we're going to test 5% significance level, whether age and movie preference are independent. Okay, so let's find out. Let's go back to our studio and get our data. Remember to enter it by column. There are 3 rows. So we take a look at our matrix and we see that it matches the one we had before. And we do the chi-square test. We get a chi-square value of 3.6229. So we did our calculation. Our chi-square value is 3.6229. Degrees of freedom is 3 minus 1 times 3 minus 1, which is 4. And therefore you get a p-value of 0.4594, obviously bigger than alpha. So we do not reject the null hypothesis that age and movie preference are independent. And you might have guessed that before we started because the age range is not that great. We have college age, recently graduated college students, and kind of, the early 30-year-olds. And although maybe the preferences might change a little bit, you wouldn't expect the preferences from this, these age groups to be different. If you put in older people, 50-year-olds, 70-year-olds, you would expect their preferences to be a little bit different. For example, drama might not be as popular among older people. And if you go to grandparent age, science fiction would not be very popular. But in this age range, it doesn't look like it affects it too much. And so you would conclude that, well, we don't have any evidence that suggests that they are not independent. All right, we'll do some examples in class. See you then.